Okay, today we have Seung-Schik Yoo. He is a professor, associate professor of radiology at the Brigham and Women's Hospital. And so he's going to reinforce a lot of the concepts that we talked about and tell us a lot more as well. So take it away, Seung-Schik.
All right. Well, thank you very much for this wonderful opportunity. I'm very thrilled to be the part of this unique and wonderful course named Intro to Ultrasound Physics and Ultrasound Neuromodulation. I am very grateful for the organizers, Drs. Kim Butts-Polly and Keith Murphy. My name is Seung-Schik Yoo, and I will talk about bimodal neuromodulatory effects of ultrasound on eliciting motor activity as well as on suppressing epilepsy. I would like to also introduce a new ultrasound technique to disrupt plasma protein binding with pharmacological agent and its potential utility for epilepsy suppression and as a new mode of neuromodulation. I do have many video clips that involve animals, so please consider being advised and see the presentation at your discretion. Before I get into the main part of my presentation, I would like to briefly introduce myself. I'm representing a group of scientists at Neuromodulation and Tissue Engineering Laboratory at Brigham and Women's Hospital, Harvard Medical School in Boston, which is known as the Stanford in the East Coast. We aim to answer two main questions. How do we change the neural function? And how do we make neural tissues in vitro? We are addressing these questions by conducting research on focused ultrasound-mediated non-invasive neuromodulation and neural tissue engineering using 3D bioprinting. These two pillars of research are supported by fMRI-based functional brain mapping and cellular imaging capabilities. I feel fortunate to work in a research environment that consists of 11 co-investigators and collaborators, 9 staff and trainees with different backgrounds. So let's cut to the chase. Why do we need non-invasive brain neuromodulation? We know that conventional pharmacological approaches for neuromodulation in general are not region-specific, and much efforts were made to develop non-pharmacological brain stimulation modalities. Region-specific neuromodulation would provide unprecedented opportunity in neurotherapeutics and may offer assessment of regional brain function with many diagnostic potentials. We have several brain stimulation techniques out there. Some are invasive, while transcranial direct current stimulation, TDCS, and transcranial magnetic stimulation, TMS, offer non-invasive options. For TDCS and TMS, the area of modulation is still quite large, about an inch and more in diameter, and they cannot reach deep brain areas. Therefore, we want both spatial specificity and deep brain penetration, and we believe that the ultrasound, focused ultrasound, we call it FUS, may provide a unique and exquisite solution. I personally believe we are in the middle of a renaissance period for therapeutic ultrasound, and much is owed to the development of transcranial FUS techniques. FUS, developed through 80s and 90s, offers delivery of acoustic energy to a small and steerable regions of the biological tissue. How small? Roughly the size of a rice grain to about the size of orzo pasta grain, depending on the system configuration. The acoustic energy is transposed to either heat, for example, to ablate uterine fibroid, or a pressure shock waves to break away kidney stones. For transcranial application of FUS, a low frequency range, typically less than 1 megahertz, is used for better skull penetration. I believe the previous lectures have discussed the rationale behind using the lower frequency compared to the one used in the diagnostic ultrasound imaging. The breakthrough was seen from the development of a helmet-style multi-array transducer configuration and independent control of each transducer element that corrects for the phase aberration, and MRI guidance is used in conjunction with the configuration in order to place the focus onto the desired location of the brain. Here is the example of such a system called X-Ablate, and I believe both Stanford and Harvard are using the system for patient treatment. On the other hand, a single element transducer can also generate an acoustic focus using an acoustic lens or a transducer that has curvature. Due to portability and simplicity, my lab is mainly using this configuration. I believe the earlier part of the class already covered the basic physics behind the technique, but I would like to briefly go over two main jargons that I plan to use in my lecture. The first one is acoustic intensity. Its unit is watts per centimeter square, and the value can be derived by measuring the acoustic pressure in pascals. Spatial peak temporal averaged intensity, represented as ISPTA, is the time averaged overall intensity of the ultrasound waves and considered an important indicator for potential heat deposition. Of course, the heat deposition is also related to the degree of absorption of the ultrasound by a specific tissue. Therefore, it is very important to understand that ISPTA is not a sole indicator of heat generation. ISPTA is derived by multiplying ISPPA, which is spatial peak pulse averaged intensity, with the duty cycle of sonication. The European limit on physiotherapy device is about 3 watts per centimeter square, while the FDA limit on most of the ultrasound imaging device is 720 milliwatts per centimeter square. Another important jargon that you will hear is a mechanical index, MI. It estimates the degree of a mechanical bioeffect, such as cavitation, being represented by peak negative pressure in megapascal divided by the square root of frequency in megahertz. Interestingly, it is unitless number, and FDA limit on ultrasound imaging device is 1.9. So how do we achieve neuromodulation? Of course, studies are still ongoing in this area, and I would like to share our experience on this. I hope the previous lectures have covered the overall hardware schematics for generation of acoustic waves, and only the example of pulsing scheme is shown here. First, low intensity focus ultrasound operating in the range of 200 to 700 kilohertz is applied transcranially as a train of pulses. You start with a specific tone burst, which is on the order of a millisecond or so. Then you repeat this rapidly. The frequency of this pulse repetition, we call it pulse repetition frequency, PRF, together with tone burst duration determines the duty cycle of each sonication. Two sets of function generators, when one triggers the other, can create many combinations of sonication parameters. Of course, amplitude modulation of sonication itself, in addition to the pulse width modulation, can also be envisioned. And I believe that other groups are working on studying the effects of pulse shape on neuromodulation as well. Here is the continuation from the previous page regarding the technique in a nutshell. First, non-thermal mechanical pressure waves are given under the image guidance, and which enables operator to locate and steer the invisible acoustic focus. For example, test sonication is applied to moderately heat the focal spot, while on-site MRI is used to measure the temperature change. If you want to avoid hitting the brain tissue, neuronavigation with additional numerical simulation can be employed to estimate the geometric location of the focus. We are currently using this approach. There are also elegant imaging solutions. For example, acoustic radiation force imaging is used to directly visualize the focal area. Dr. Buzz Pauli is one of the world-leading pioneers in this field. People are working on increasing the sensitivity of the technique in order to use it at low acoustic pressure. Through the research, we found either stimulatory or suppressive effects are observed using different pulsing schemes. So the jury is still out about exact parameters to do this, but stimulatory sonication utilizes a high duty cycle and short sonication duration at higher acoustic intensity, but still low compared to the high intensity focus ultrasound for tissue ablation. whereas suppressive effects are seen at lower duty cycle and longer sonication duration given in lower intensity compared to the stimulatory parameter. I would like to emphasize that studies are ongoing to find the exact mechanism and the parameter to achieve this neuromodulatory effects. So let's talk about motor control by first stimulation. And this slide is simplified illustration of human brain motor pathway, which is also referred to as cortical spinal tract. Please remember that there are similarities and differences in the neuroanatomy depending on the species. Over the half of the neural bundles originate from the primary motor cortex, we call it M1, located in the precentral gyrus. The remainder rise from the premotor or supplemental motor area, which is located anterior to the primary motor cortex, and also from the parietal lobe as well. The primary motor cortex neurons make connections to the motor neurons in the spinal cord, as well as onto the spinal interneurons through the cerebral white matter tract, namely the corona radiata. On its way down to the spinal cord, the pathway goes through the internal capsule and connects to the thalamus on the same side. The thalamus is considered as the switchboard for the brain, relaying information among different neural circuits. I would like to remind you that the most of the signal pathway crosses the hemispheric midline in the medulla of the brain, a structure called the pyramids, and the rest of the pathway crosses at the spinal cord level. In all, the activation of one hemispheric motor area creates the effective muscle movement in the opposite side. Back in 2007, we conducted a series of experiments on New Zealand white rabbits to stimulate their motor area using focus ultrasound. A 690 element ultrasound transducer with 8 centimeter focal depth was used to apply FUS under the guidance of MRI. The sonication was given from the water bath below the head, and the mechanical stage was used to adjust the location of the transducer. The target was unilateral side of the sensory motor area of the brain responsible for the motion of their forepaw. Real-time functional MRI, we call it RT-fMRI, and electrophysiological recordings such as EEG and electromyography were used to characterize the spatial temporal feature of activation. Blood oxygenation level dependent, in short BOLD, fMRI signal was used to measure the brain activity. The red line is the signal from the sonicated motor area, while the blue indicates the signal from unsonicated area. During the acquisition of fMRI, we encountered the BOLD signal spikes from the sonicated motor cortex upon the application of 1 second long FUS with tone burst duration of 50 milliseconds given at a pulse repetition frequency of 10 Hertz. The duty cycle was therefore 50%, and the maximum ISPTA was 6 watts per centimeter, was about, actually this is a typo, it's a 6 watts per centimeter square with corresponding mechanical index of 0.5. Continuing from the previous slide, this figure shows the spatial pattern of brain activation as revealed by fMRI, which coincided well with the sonication target in the motor area.
Seung-Schik,
Yes.
one of the things we talked about earlier in the class was that the confound with anesthesia, and especially fMRI is very, very sensitive to anesthesia. So could you just tell us what kind of anesthesia did you use for these experiments?
Oh, that's a good question. Yes, we used a combination of ketamine and xylazine. So that's what we used, and in other studies, we actually compared the effects of isoflurane and ketamine and xylazine as well. And for later experiment in sheep as well, we'll cover later on, we used the tilamine for anesthesia.
Seung-Schik, off of just sort of your perception, are there differences in how those anesthesia affect your ultrasound response? Because Scott Hansen in one of our prior lectures had talked about that.
Right, I do agree. Although we didn't really cover it in my presentation, my experience is that isoflurane is definitely affecting more than ketamine and xylazine, at least for the rat. So as I'm going to cover it later on, a lot of our current effort is moved to study the ultrasound effect on awake and unanesthetized animals as well. So you will probably going to see for the later part of the presentation that we will actually conducted a study without using anesthesia. All right, let's move on. So we just talk about this figure that the pattern of functional activation observed by fMRI is well coincided with the site that has been sonicated, suggesting it has been indeed stimulated. And let's see this video. This video shows the result from stimulating the motor area of the rabbit. And the sonication was given to the left motor cortex. And as you can see, the twitch of both front legs with a greater degree of motion in the right. Then we move the transducer to stimulate the right motor cortex. And also we decide to reduce the intensity. The stimulation resulted in a smaller movement, but more distinct motion toward the left forepaw. We are not exactly sure why unilateral stimulation of a motor cortex elicited the movement from both limbs, but we hypothesize that it may be due to the highly interconnected motor area of the both hemispheres. A similar bilateral activation of the hand motion has been observed from TMS stimulation in humans as well.
So Seung-Schik, even though your forepaw, both paws are moving in response to unilateral stimulation, the bold signal only shows up on one side of the brain. Is that right?
That's correct. That's correct. So we were anticipating some type of co-activation of the both hemispheres, but we didn't really see that. Probably it was related to the different acoustic intensity that has been used to detect the forepaw movement, as well as can be used, as well as compared to the one that used in the fMRI. So I think that could be the contributing factor as well.
Mm-hmm.
So being motivated by this finding, we moved on to stimulating motor areas in rats. And we used a similar experimental setup as the rabbit, but now the ultrasound was coupled to the head using a plastic bag containing degassed water. These video shows that the fuss applied to the motor area of the rat brain related to the tail or the forepaw can elicit corresponding motor responses. As we briefly talked about, anesthesia in the context of animal research, which is unavoidable, provide unavoidable confounders in brain stimulation. So therefore, research in awake animal was also necessary, and wearable fuss device was also needed. So in order to stimulate the brain while the rats are awake, we made a miniature wearable single element transducer, which weighs about 9 grams. And due to the small size, about the size of a digit of a finger, we applied the transducer through the pedestal implanted over the rat's head, while the 3D printed applicator was used to steer the focus. The actuating signal was delivered through the swivel connector that is located above the cage, and the sonication was coupled using compressible hydrogel. We demonstrated that fuss can stimulate selective motor areas in awake state, and additionally, we observed chewing or head nodding behavior, as you can see from these movie clips. We have been working on conducting a similar study in awake sheep as a large animal model. To conduct study in an awake sheep, we designed a wearable fuss headgear, which can place an acoustic focus on the desired brain location. And we investigated the bimodal effect of fuss by detecting electromyography from both hind limbs. A series of acclimation and training were given to make sheep walk on the treadmill, wearing a custom-made headgear that is linked to the fuss transducer. Tattoo markings, there are 3 tattoo markings, were applied on the scalp to provide reproducible landmark coordinates for placing the headgear. And we obtained MRI data for image guidance. Functional MRI was also performed to identify the motor area while their right hind limb was mechanically stimulated. Prior to FUS experiment, the headgear was aligned with respect to the tattoo markings and strapped over the head. We used a single element transducer with focal length about 3 cm, operating at 250 kilohertz. And this plot shows the intensity profile of the focus as separately measured in a water tank using a hydrophone. For excitatory sonication sessions, sheep stayed still while EMG was obtained, and we applied a set of parameters for excitation as optimized from experiments from anesthetized sheep. For excitation, tone burst duration of 0.5 millisecond, sonication duration of 200 millisecond at duty cycle 70%, and in situ ISPTA of 11 to 14 watts per centimeter square were used. We applied the 3 experimental conditions, which were on-target stimulation of primary motor area and the thalamus, off-target, and last, no sonication. For off-target conditions, sonication was delivered to the area about 1 centimeter posterolateral to the primary motor area, and multiple stimulation sessions were administered with total number of stimulation close to about 260 per each sheep. The acquired raw EMG data was filtered, rectified, and temporarily smoothed, and the DC signal offset was removed as described here. And here is the time-locked group averaged EMG signal obtained from different conditions. The red line indicates the EMG signal contralateral to stimulation, while the blue indicates the one from the ipsilateral side. Stimulation of the M1 and thalamus selectively yielded group-level elevation of EMG signal amplitude from the hind limb contralateral to sonication compared to the one from the ipsilateral side. For both off-target and without any sonication, EMG responses were not observed. These data suggest that selective activation of motor area is possible in awake sheep. None of the animals showed visible movement of hind limb elicited by the sonication. Absence of overt muscle movement requires further study to explain the discrepancy from the small animal studies. Let's switch gear and let's take a look at the suppressive effects of sonication on brain activity. This is the result from our earlier work on New Zealand white rabbits. Like before, using the same experimental setting, we used 690 kilohertz focus ultrasound to sonicate the visual area of the rabbit under the guidance of MRI. We measured the bold activity from flickering light induced activation of the visual cortex to characterize the spatial temporal feature of activation. Light-induced activation in the visual cortex was selectively decreased by application of a 9-second long FUS having 0.5 millisecond tone burst duration given at the rate of 100 hertz. The duty cycle was therefore about 5%, and the maximum ISPTA was 0.16 watts per centimeter square, and mechanical index was 0.5. This is the continuation from the previous slide showing the evidence of suppression of cortical activation by FUS. The external visual stimulation was given to establish the baseline brain activity during fMRI data acquisition. The area of activity from the visual cortex, shown in red, diminished right after applying focus ultrasound, but reappeared when sonication stopped. The plot on the right shows the time progression of a bold activity for different experimental conditions. The green bars indicate the activity when there was neither the visual nor the FUS stimulation, whereby the bold signal stayed flat. The red bar indicates the bold activity from the visual cortex in the absence of sonication, which also, stayed flat while it was definitely more than the baseline. As shown in blue bars, bold signal upon the application of FUS decreased temporarily, but recovered in a few minutes later. The suppressive effect of FUS in rabbit was also confirmed by the visual evoked potential, VEP measurement, which is a type of EEG measurement on brain activity responding to external light stimulation. The sonication knocked down the EEG activity shown in red, especially the positive peak that appears at 30 millisecond latency. As you can see the time plots on the right, the reduction in VP peak was recovered back to the baseline in about 10 minutes after the sonication. Now, armed with the ability to suppress the regional brain activity, I would like to talk about epilepsy suppression using ultrasound. Epilepsy is caused by uncontrolled hyperexcitability of the neural tissue in the brain and causes different type of behavior, cognitive and mental manifestations, including seizures. The Epilepsy Foundation website offers rich information for general public. Epilepsy can be roughly classified according to where it comes from. First, focal epilepsy, which means that uncontrolled excitability is generated from a regional brain area. Generalized epilepsy, which means that it comes from many parts of the brain. And last, the epilepsy with unknown spatial origin. Epilepsy is the fourth most common neurological disorders, affecting more than 200 new cases per year in the United States alone. So we decided to test whether or not the suppressive sonication delivered to the red thalamus can reduce seizure caused by chemically induced epilepsy. To induce epilepsy, pentylentetrazole, PTZ, which is a very potent GABA inhibitor, was injected to a rat. And this movie clip shows the actual demonstration of this feature. The sonication was given underneath the water bath, shooting upward toward the rat brain, and we monitored the EEG. These are the EEG electrode wires, and let's watch what happens. The rat developed epilepsy and seizure within about 5 minutes after the injection of PTZ. As the PTZ acts on many parts of the brain, therefore the creation of focal epilepsy was not possible. We decided to target the thalamus, whereby the thalamus serves as a main switchboard for the brain. So we delivered suppressive sonications to the thalamus for about 1 minute. And sonication was started. For about 10 seconds or so, nothing seems to work. But as you can see, in few seconds later, you can appreciate the seizure activity significantly decreases. Because it is very challenging to extinguish the seizure that is caused by PTZ, my colleagues jokingly told me that we killed the rat. Of course, we did not, and then rats were just doing fine in the next day. Although not shown, if you stop the sonication, the seizure activity eventually comes back. But this is a dramatic demonstration of very potent suppression of regional brain activity by applying FUS. So here's the actual EEG recording from the rat. These big spikes, EEG spikes, indicate the state of epilepsy, and the bar indicate the duration of application of ultrasound, which is given to the thalamus. Upon application of FUS, the EEG amplitude progressively decreased, which indicate the hyperexcitability was somehow suppressed.
Seung-Schik, could you quickly comment on the nature of epilepsy and why it causes these high amplitude spikes, just so the audience has sort of an idea of that?
Right, so let's start with the EEG itself. So EEG is a device that measures the electrical potential differences that is caused by the neuronal activity. You typically measure it over the scalp. You don't really, there's a version of EEG that you can actually implant the EEG electrode, but that's an invasive procedure. And as you could see, the electrode was actually attached to the scalp, and you are measuring the differences in the electrical potential movement vectors, just like the EKG that you measure the electrical activity from the heart, but now from the brain. And epilepsy, as you can see from, could review from these three different origins, roughly, it is causing the hyperexcitability of the neuronal tissue. And this hyperexcitability that is comes in as a spikes and burst of a flow of electrical currents induces a detectable EEG signal that is represented as a big spikes. And the degree, as you can see from this slide, depending on the type of epilepsy, the EEG spikes looks different as well. So that's how it goes. So let's move on to this. I think this slide actually can show you another example of how the EEG may look like. But again, I would like to emphasize that it is an EEG signature that is obtained from the rats, and the human version of EEG could be a little bit different. And also it depends on the number of EEG electrodes that you use. So therefore, the interpretation of EEG that is related to the epilepsy could vary according to the species as well. So after the experiment, we also tested whether or not the FUS can suppress the chronic epileptic activity with a focal origin. To generate focal epilepsy, we injected cyanuric acid, a seaweed-derived glutamate agonist, directly to the hippocampal area to the rat using microneedle. Then it takes several weeks to develop epilepsy, but the time investment is worthwhile because this technique can create a condition that resembles human version of focal mesial temporal lobe epilepsy. We call it MTLE. So after confirming that rat develops epilepsy, we aim the sonications to the hippocampal area under the monitoring of EEG. As you already recognize from this plot, the EEG signature is bit different from that of PTZ-induced acute epilepsy, which consisted of a fewer but stronger spikes in the EEG. So after detecting the epilepsy, we applied FUS for about 1 minute, and this did not extinguish the ictal activity. So we gave another one a few minutes later. Ictal activity was reduced in occurrences, but still remaining. And the third application of ultrasound finally knocked down the ictal activity from this rat. So motivated by this finding, we are currently working on enhancing the suppressive effects of FUS on focal epilepsy through rodent model. And there are ongoing clinical trial at Brigham and Women's Hospital to suppress the drug-resistant epilepsy in human patients. Apart from epilepsy model, here is our recent experience from sonicating the awake sheep to suppress the regional brain activity. Like before, we used a transducer with a focal length about 3 centimeters operating at 250 kilohertz and applied a set of parameters that is described here. Please note that we are using lower duty cycle of 5% at longer sonication duration of 1 minute compared to the simulatory counterpart. This time, sheep walked on the treadmill for 5 minutes, and FUS was delivered for 1 minute after establishing the baseline EMG level. And as previously described, we gave 3 experimental conditions, which were on-target suppression of the primary motor area and the thalamus, off-target, and no FUS. We found the sonication successfully reduced the EMG tones while the sheep were walking on a treadmill. The bar indicates the EMG signal amplitude measured and averaged every 30-second segments in time, normalized with respect to the pre-sonication baseline level. So red bar indicates the value from the hind leg contralateral to sonication, and the blue bar indicate the one obtained from the ipsilateral side. As you can see from these plots, sonications to the M1 and thalamus temporarily reduce the amplitude of contralateral EMG compared to the one from the ipsilateral side. During off-target and no FUS condition, the EMG remained unchanged. We are currently analyzing if there was any disturbances in their gait induced by the sonication. So let's look at the potential mechanism. Unfortunately, it is not clear, but first we excluded the contribution from the contribution of changes in tissue temperature, since we have not seen any temperature rises due to sonication. It is not electromagnetic, these effects has been observed regardless of the presence of a MR environment. And therefore, we believe it is mediated most likely by mechanical energy. For example, FUS induces a mechanoreceptor and ion channel activity. It may change cross-membrane capacitance and alter the excitability. It can also stimulate the glial system through calcium signaling pathway. For quick diversion, I would like to talk a little about the glial system of the brain. The word glia comes from the Greek word glue, and there are more glial cells in the brain, at least 7 to 8 times more than the number of neurons. So departing from the classical role as a supporting cells in the brain, the recent studies have revealed that the glial cells play a very important role in neural signal transduction and communication. In addition to potential effects on glial system, FUS can also stimulate group or ensembles of inhibitory versus excitatory neurons, resulting into different tissue level responses. And furthermore, we have shown that FUS may modulate the neurotransmitter activity. In summary, there could be multifaceted mechanisms behind neuromodulatory effects of ultrasound. Based on exciting properties of focused ultrasound, here are the list of current and planned research projects. We are conducting research on large animal model, sheep, testing in stimulating and suppressing somatosensory and thalamic areas using wearable FUS system as funded by NIH. As funded by NASA, we are also conducting research on the application of FUS to stimulate somatosensory cortical and thalamic areas among healthy volunteers to assess its safety and effectiveness. We ultimately aim for non-pharmacological neuromodulatory interventions for astronauts during deep space exploration, whereby the astronaut may not have adequate medication supplies. We are also working with the Defense Health Agency and Spalding Rehab Hospital to apply the technique to stimulate a primary motor area and premotor area for enhancing motor skill learning. So here are the overall design elements for human applications. First, we acquired neuroanatomical information in the form of MRI, fMRI, and CT to make a virtual space of an individual. Then we co-registered the physical and virtual space and used neural navigations to provide the operator with a real-time update on the position and orientation of the FUS transducer. This ability is further backed by high-speed numerical acoustic simulation to estimate the location and intensity of the focus. Let's look at another strategy to modulate the brain function by disrupting blood-brain barrier, BBB. Unlike blood perfusion elsewhere in the body, the BBB, a strongly needed endothelial wall of the brain blood vessels, acts as a tight barrier to limit the delivery of large molecules and foreign particles into the brain tissues, adding a protection to sensitive neuronal cells. While this protection is generally good, it becomes problematic when you want to deliver therapeutic medications to the brain tissue, since the BBB will also block the passage of many types of medication that is greater than typically 400 to 500 Dalton in their size. FUS can help in this scenario as well. The ultrasound is applied conjunctionally with intravascular injection of microbubble ultrasound contrast agent. And these bubbles are used to enhance the ultrasound imaging quality for liver or kidney imaging. The ultrasound induces a cavitation of injected bubbles, and cavitation refers to their stable wobbling. And this wobbling motion amplifies the regional acoustic pressure waves. In turn, the amplified pressure waves are believed to loosen the adjacent endothelial connectivity, temporarily disrupting and opening the BBB toward larger molecules, including medications. So we applied the technique to a ovine model, sheep, and injected gadolinium-based MRI contrast agent and performed dynamic MRI-based pharmacokinetic analysis, which showed that the local disruption of a BBB is illustrated in red color. We believe that this technique may be used to enhance the delivery of a neuromodulatory drug, and I believe there will be more further detailed discussion and presentation about this technique regarding disrupting the BBB using ultrasound. While the BBB is well-known physical barrier in drug delivery, there is also well-known but often forgotten functional barrier. This is called plasma protein binding, PBB. Plasma proteins play a key role in regulating the pharmacological activity of many types of drug in the body. The efficacy and toxicity of a drug is significantly impacted by the fraction of the drug in the blood that is unbound to the plasma protein. For example, albumin and alpha-1 acid glycoprotein. These plasma proteins are quite big, greater than 41 kilodalton in their size, and therefore cannot cross the BBB. So you may imagine that these drug molecules would, drug molecules would stick to plasma proteins just like dust sticking to a duster. And these proteins will keep the portion of the drug within the bloodstream, preventing their action. The degree of binding is drug specific and determines the pharmacokinetics of the drug. But I would like to let you know that there are many drugs that bind more than 80 to 90% to the plasma protein. So therefore, it is important to understand that in general, we need to take more drug than really necessary in order to feed the organs and the tissue at the right level.
Seung-Schik, I have a bizarre question, but is the natural purpose of these plasma proteins to bind toxins in the blood? And as if all drugs are like toxins, sort of?
Well, that's very interesting comment. It could be, but as I'm going to explain in this slide, the proteins, depending on the type of the drug, whether it is basic or acidic, I mean, the non-covalent electrostatic or the van der Waals forces, according to their interactions between their molecules, between the drug and the plasma proteins, they somehow create this attractive force. It's not only happening between the drugs and the plasma proteins, but it also happens in different part of innate the molecules in our own body. So therefore, I don't think it is 100% defense mechanism per se, but I believe it is a natural phenomenon that is occurring in our own body and happen to be, it applies to a lot of different drugs. And as I talked about before, the forces that governs the binding are non-covalent electrostatic and van der Waals forces, which are very weak, on the order of a piconewtons. So if a sustained mechanical force, for example, generated by a focus ultrasound, which is strong enough to overcome these binding forces, it may disrupt these weak interactions temporarily and lead to unbinding of the drug from the plasma proteins. As a result, the local concentration of unbound drug will rise temporarily, but consequently will be available to cross the intact BBB without alleviating the systemic drug dose, as well as associated risk of side effects. Well, caveat here is that this technique will only work for drugs that bind heavily to plasma proteins. But please remember that roughly 1/3 of all medications are subjected to a high level of a plasma protein binding one way or another. To implement this idea, we first targeted albumin-phenytoin interaction. So phenytoin is a common anti-epileptic, anti-seizure medication, small enough to pass through the BBB, but sticks really well to the plasma protein, primarily to albumin. So we conducted an in vitro experiment to sonicate the aqueous solution containing phenytoin albumin mixture, simulating the phenytoin in the blood, and measure the unbound phenytoin that passes through the dialysis membrane after unbinding. These small little green boxes are called equilibrium dialysis cassettes, and each collects a specific size of molecules through its membrane. So we found that the concentration of phenytoin from the sonicated cassettes were elevated compared to the one outside of the focus or without sonication, suggesting that phenytoin was indeed unbound from albumin by the ultrasound. So motivated by this finding, we applied the sonications to the rat brain that received the phenytoin and performed immunohistochemistry, IHC, on the extracted brain. The phenytoin appears as a darker brown hues in the IHC. And this dotted line indicates the location of acoustic focus. The grayscale image on the right shows the increased phenytoin uptake around the acoustic focus. Trypan blue IV injection showed no staining, indicate the intact brain barrier. If the BBB was disrupted, the brain will show blue hue staining everywhere. So these findings suggest the ability of focused ultrasound to locally unbind the phenytoin from albumin and increase the uptake of phenytoin across the intact BBB into the brain parenchyma. Here's a list of projects that are related to unbinding of pharmacological agents by application of ultrasound. We recently started a project to enhance the effect of phenytoin in suppressing rodent model of a mesial temporal lobe epilepsy. And we believe that these effects can be expanded outside of the realm of neuromodulation. For example, we are conducting research on enhancing the effect of finasteride in treating male pattern baldness using mice model. Finasteride is strongly binds to albumin, while it blocks the formation of dihydrotestosterone, DHT, which is a main hormone for male pattern baldness. On the other hand, lidocaine, a local anesthesia, binds to alpha-1 acid glycoprotein, and we are working on enhancing the effects of lidocaine in reducing the peripheral pain. We also would like to enhance the effects of paclitaxel for cancer treatment. Paclitaxel, a potent anti-tumor agent, heavily binds to albumin. And we aim to locally increase the drug level without elevating the systemic dose, which accompanies many side effects.
Seung-Schik,
Yes.
in these applications, then the use of ultrasound is mainly to overcome that plasma protein binding. I'm wondering, is it critically important to have the focusing at the target location, or can the focusing be relaxed so that you get extra drug in normal tissue?
Right, that's really excellent question, Kim. As Kim said, exactly, it will be depending on the location of the unbinding will happen, right? So therefore you can relax it, relax the being able to focus ultrasound into specific location. For instance, if you want to relax the focus into the more to cover wider area, you can probably increase the area that is being treated, for example. But also you can go very small target as focus ultrasound can do. So therefore, yes, obviously depending on the aim of the study or what you want to do, you can use a different type of transducer, and therefore that's the size and location of the focus itself.
Yeah, just kind of a related question is, what's sort of the time course for the binding and unbinding?
Right, that is another important question. So one thing I would like to tell you is, I'm going to go back and just look at this illustration. This unbinding and binding happens all the time because without any application of ultrasound, because it is governed by such a very low for the amount of forces. So therefore, this binding and unbinding happens so quickly without any external forces to begin with. And if we apply the ultrasound, it is temporarily release more, I would call the dust in a way. I'm just going to put the analogy. But if you stop the sonication, the dust will be basically stick back to the duster. So this effect will be temporary. And I think we heard that these interactions happen so quickly. So therefore, you have to kind of sustain the application of ultrasound. So if I want to put into an analogy, you have to kind of keep shaking the duster, to separate dust out from the duster. And you are using this time frame to hopefully to move your medication of interest across the BBB and have a time to allow this drug molecules to have an effect on the parenchyma.
Yeah, and sorry, so just another related question is, so not only would the ultrasound potentially relieve the dust from the duster, as you say, but it could also push the molecules towards the endothelium cells. So I wonder if you've thought about sort of how big an effect that is versus the binding unbinding effect.
Oh, that's another golden question. I am very interested in studying that phenomena. So you can imagine that is just regular type of medication that you may imagine, but I do believe that it will have some forces behind any molecules, including the molecules that are existing in the brain itself. You don't have to, it does not have to be a drug per se. So I think the jury is still out in this investigation, but I do believe there is probably some effect of more of a bulk flow or convection that could be created by application of ultrasound. Very interesting aspect, and I think we need to study that.
Mm-hmm.
So here's the summary. Focused ultrasound may make pharmacological approaches indeed region-specific in a way, and thus may provide a unique but multifaceted opportunities in neurodiagnostics. I personally believe the FUS can also be used as a complementary technique instead of being competitive to existing brain stimulation modalities. More work is needed to reveal its true potential in terms of safety, brain stimulation, ability to modulate myelinated nerves, and to disrupt the BBB, as well as to change the pharmacokinetics of a CNS drug by disrupting the plasma protein binding. Here are the list of a link to the recommended literature from my lab. And I would like to acknowledge the collaborators and lab members as well as funding sources. I hope I will see you in person someday. I really do. Thank you very much.
Great. Thank you so much, Seung-Schik. There's so much that was really just so fascinating in your presentation. I feel like I asked a bunch of questions. Maybe Keith, do you have a question right off?
Yeah, just to refer back to the plasma protein binding project, which I'm just absolutely floored by. It's incredible. I'm sure everyone's asking whether or not you can design all drugs to have a binding site for something like albumin so that you can really design any drug that anyone wants to use to be spatially and temporally specific, which again, I'm just floored by that project and I think it's amazing.
Well, thank you very much. That's really interesting comment. So people are working on a designer type of designer drugs, they call it. It could have a different meaning, but it could have a different type of binding forces with the protein binding, plasma proteins. I mean, albumin is a big hurdles for many types of drugs, and people are trying to actually use albumin as a drug delivery vehicles. For instance, paclitaxel, they actually come up with this large albumin chunks that has many albumin molecules in it as a sphere, and then you can actually embed the paclitaxel on the surface and inside. So instead of being having paclitaxel be attached to the albumin during the delivery, you can actually embed it in the beginning, let the cells to uptake this albumin chunk, and then deliver paclitaxel into the intracellular space to do its action. And also, obviously, you can think about some future potential technique that you can design and tailor the location and degree of binding. But yet, I think there are a lot of other work to do to have that much of a spatial selectivity. So obviously, that's really a good comment, and I appreciate that. I love to study more about that.
Mm-hmm. And we look forward to hearing it. I had sorry, Kim, I just had one more question, then I'll go back to you. So the students, as you know, are learning how to design experiments as they go through this course. And something I noticed that you give a lot of attention to, and I think it's really important, is using the contralateral and ipsilateral sides of the brain as almost controls for them, for the brain itself. I was hoping if you could just elaborate, why you think that's important and when it may not be appropriate in terms of the connectivity between the two sides of the brain.
Oh, that is really fantastic question. Thank you very much. We are always in conflict when we design the experiment. So, I mean, for classical neuroscience, the neural circuitry dictates that, well, if you stimulate one side of the brain, it will usually go to the other side. Although we know there is an interconnection between the hemispheres, but the stimulation of one unilateral brain motor area, for instance, is mostly and primarily linked to the area that is in the opposite side. So we kind of tend to think that at least we should examine the effects from sonicating the other, the side that has not been sonicated, and compare with the efferent pathway that is being sonicated. It appears that it almost acts as a control, but I don't think it is fair to call it as a real control in a way, because as you might see from my presentation in the rat, you actually see a bit of bilateral activation of this of the rat's forepaw when we actually stimulated only one side of the brain. And as I previously discussed, when you stimulate the human unilateral motor area, it could elicit the activation and movement from both hands. So therefore, we should look at both sides of the like, for instance, motor efferent pathways, if you want to go for stimulation of ipsilateral brain area. But depending on the species and outcome, you should analyze it as it is and examine the connectivity between the two. I mean, you can bring in a lot of different other modalities. For instance, the fMRI is a good example. You can examine the activation from potentially across the brain area. And I just also is a link to your previous question that why didn't really see the bilateral activation from the rabbit. We only saw unilateral activation. We saw a little bit of bilateral activation in the opposite side, but I think we should spend more time and studying a little further. And obviously, I really hope to see this phenomena more on in non-human primates or in healthy volunteers as well, because it's the neuroanatomy, depending on the species, is vastly different.
Yeah, I have a question. You know, the anesthesia question is something that we just really struggled with over and over with animal experiments, and I didn't realize that xylazine ketamine would still allow you to do an fMRI experiment. And I often wondered, Seung-Schik, with your rabbit experiments, whether you weren't taking advantage of the fact that there's this phenomenon with some animals, and I think it's true with the rabbits, that if you put them upside down, you can sort of hypnotize them without any anesthesia. And so I often wondered if that's what you were doing in order to get the fMRI to work.
Oh, wow, that will be interesting. I thought that the sharks, you can do that, but I didn't know that you can do it with the rabbit. I really wanted to learn the technique from you. But yes, it is still an important factor. Ketamine and xylazine versus isoflurane, or even different type of anesthesia. I mean, being able to interrogate the effect from the anesthesia in conjunction with different techniques such as fMRI, which actually is governed by different hemodynamic responses due to the brain stimulation. I think we definitely need to look into further. But I would like to declare that we didn't know how to make the New Zealand white rabbit to go into this anesthetic state by just flipping around.
All right, I think we need to conclude. Keith, do you have any last questions?
I'm good. Thanks so much for that, though.
Thanks so much, Seung-Schik.
Thank you.